So for this example, we have that the length x of rainbow trout in a particular fishing hole has an expected value of 35 centimeters with a variance of 10 centimeters. To translate to inches, sorry, I have to sneeze. Let y equal 0.39x. What are the expected value, variance, and standard deviation of the rainbow trout length in inches? Okay. So to start with, we know that the expected value of x equals 35 centimeters, and the variance of x is 10 centimeters. And what did I say unit should be on variance? Variance always has units squared. That's why we actually prefer the standard deviation, because it has regular units. So that was a typo. So the variance has 10 centimeters squared. So we want to find the expected value and variance of y. Okay. So the expected value of y, that's really the expected value of 0.39x. Okay. So what happens to that 0.39 for my expected value? Okay. I want to bring it out. For expected value, does it come out as it is, or does it get squared? Expected value just comes out as it is. So we just pull out the 0.39 times the expected value of x. So really this is 0.39 times my 35. Gives me 13.65. So for this fishing hole, the expected length of the fish you're going to catch is 13 inches. So on average, if you catch a lot of fish, the average length should be 13 inches. What about the variance? Okay. So this is the variance of my 0.39x. But if I want to pull out a coefficient for variance, I need to square it. So we pull out my 0.39 squared times the variance of x. So 0.39 squared times 10 is 1.521. And to find my standard deviation, I take the square root of variance. So 1.23 inches. So for this fishing hole, my average length will be 13 inches, and the standard deviation in the lengths of the fish that I catch will be 1.23 inches.
If the original information was given in centimeters, do we also need to convert between centimeters to inches, or is it automatically inches?
Well, that's what happened when we converted right here.
Oh, okay.
And so we're converting our centimeters to inches.
Okay.
So for our next example, remember that we have our judge one prison terms example. Okay, in example 3. Suppose that we randomly sample 10 sentences given by this judge and record their total length. So will you look back to example 3 and let us know what the expected length was? $2.25, and did we ever find the, I'm pretty sure we found the variance of them at some point. What was the variance?
That's 1.
Uh-huh. Did we find the variance for him?
0.3375.
0.3375? So we knew it, so we looked at it and we said for this judge, the expected length of sentences is 2.25 and the variance is 0.3375. Okay, now that is for one sentence. Okay. But here we want to find 10 sentences and record their total length. So what am I really doing here? Okay, so that's going to be my shortcut in a moment, but what am I actually really doing? I am adding 10 of them together. Okay, so I'm going to show you in a minute why that makes a difference. It's something that, so I also teach this as an online class, and they started a month earlier, so they're a little bit further ahead, and they really had trouble with this concept, what I'm going to show you here. So it's important to make sure you know what you're doing. So we're looking for the expected value of x1 plus x2 plus ... up to x10. So we are adding 10 sentences together, and we want to look for the expected value of this combined length. Okay. And what did we say we can do for expected value if we're adding random variables together? Okay. As far as expected value rules, if we're adding things together, we can just add their individual expected values. So this is expected value of x1 plus the expected value of x2 plus ... up to the expected value of x10. And what is the expected value going to be for each one of these sentences? It is going to be 2.25 plus 2.25, and it turns out, how many times did I add it up? 10 times, so it's 10 times 2.25 gives me 22.5. So the expected length for 10 sentences, the total length for 10 sentences is 22.5. Now, at the beginning, I heard you guys saying you just wanted to multiply it by 10 at the beginning. Okay? And that was natural because you realize at the end I'm going to add them up, and so it's easier to just times by 10. But it does make a difference when you get to the next part. So when it says, what is the standard deviation of their combined length? Do we have any formulas for finding rules for standard deviation? No, we only have formulas for variance, so we need to find the variance first and then go back to standard deviation. So we're looking for the variance of, again, x1 plus x2 plus ... up to x10. Okay. Now, we have the rule that says if these are independent random variables, then I can just add the variances. Now, I didn't specifically say that these were independent, okay? But as long as you didn't have a couple people going in together that we sampled, since we're randomly sampling, we should get people that were non-associated with each other. So we can assume that these are going to be independent without getting in too much trouble. Okay, if we're randomly sampling people, these people should be independent of each other. So we can write this as the variance of x1 plus all the way up to the variance of x10. Okay. Now, what is the variance for these going to be each time? It is going to be the 0.3375. And so what do I really have here? I have 10 times 0.3375, so 3.375. So the variance for their combined length is 0.3375. And the standard deviation is the square root of that. .83.
So that first variance, 3.375, is that in years squared?
This, yes, would be in years squared.
So then do we have to multiply, well, because it says in months for the standard deviation, so.
Okay, so when we get to step 3, we're going to use our rules that we learned. Okay, let me take a side note here for a minute and show you. So again, this is the common mistake that I know people made because they made it very recently. Okay, so this is what they wanted to try. They said the variance of x1 plus x2 plus up to xn. They said, oh, there's just 10 of them, and I'm adding them together, and they wrote it as the variance of 10x. Okay. Now, using our rules, what has to happen to that 10? It comes out squared. So this would be 10 squared times my 0.3375. Notice, is that going to be a different answer than what we just got? Okay. This is the key thing here. They said, well, if I'm adding up 10 variables, that's the same thing as timesing my variable by 10. But it's not. Okay. This does not work. So make sure that you don't do it and you don't try and take too many shortcuts. If it says add, then add your variances. Okay. The reason it's not the same is let's picture this as, well, let's do it in the context that it's actually in. So there's a difference between adding up 10 people's sentences, because one person's sentence might be like 1 year, one person's sentence might be 3 years, 4, 2.5, etc. So you can have different values for each of these sentences, and then you're adding them up. This way says you took just one person's and times them by 10. Okay, so if the first person got 2.3, then you would say the total combined length is 23. Okay. But that's not necessarily true, because one person might have had like 2, one person might have been 5, one person might have been 1. So you can't take that shortcut. We're not timesing one person by 10. We are adding 10 different people. So just as a side note to make sure that you're aware of that when you do your homework, and of course for the test and everything else, that you need to actually, if you're adding random variables, you need to actually make sure you add their variances. Now for problem 3, what is the expected value and standard deviation in months? So we need to translate from years to months. How do you go from years to months? Okay, well, let's see. So I want to find months. So months equals what for years? How do I write my formula to actually get months? Or I guess you said it right the first time. So months equals 12 times years, right? So if I want the expected value for months, this is the expected value of 12 times years. And what happens to that 12? Just comes out. So 12 times my expected value that I found for my y, which was my total length. I guess I never said y is my total length anywhere, did I? So let's say y is my total length. So 12 times my 22.5. $270 months is the total length for these 10 people. And the expected value, or the variance, is going to be the variance of 12 times the total years. And what happens to that 12? It has to come out squared. And what is my variance for y? My total variance was 3.375. So 486. And how do I find the standard deviation? I ran out of room, but how do I find the standard deviation? Take the square root. So my standard deviation is 22.04. So we've gone through several questions of using these rules to find our new expected value and variances. Questions on them? So now we're going to derive a very famous result, okay, that we're going to use over and over in this class. Okay. So suppose that x1, x2, up to xn is a sequence of independent random variables. Okay. Each with expected value mu and variance sigma squared. Okay, we define the average. How do we always find an average in a class? We add them up and divide by how many there are. Okay, so the average is defined as x1 plus x2 all the way up to xn divided by n. Okay. Again, so these are each random variables and they are independent of each other. We want to find the expected value and variance of our mean. So we need to find the expected value of x bar. Well, let's start by saying, well, what is x bar? It's x1 plus x2 up to xn all over n. So, what do you start thinking of when you look at this as far as the rules that we know? Like this n, is that a random variable or a number? Or like a constant, I guess. Okay, it's a constant or a number, and so what do we got to do with that for an expected value? Pull it out. So this is 1 over n times the expected value of x1 plus x2 up to xn. Okay, so I just pulled out my 1 over n. And then as far as expected value, what do we do when we are adding up random variables inside my expected value? We just add up each of their expected values, right? So this is expected value of x1 plus the expected value of x2 plus all the way up to the expected value of xn. But what is each of their expected values? Okay. If you look up in the problem statement, they all have expected value mu. So the expected value of the first random variable is mu. The expected value of the next one is mu. Up to the last one, the expected value is mu. Okay. How many of those mu's am I adding up? N of them, so I could rewrite this as n times mu. And what happens with those n's? They cancel out, and I'm back to mu. This is very interesting. So this says if you start with a bunch of random variables that have a mean, and then, so they have their expected value or their mean of mu, and then you take a mean, the sample mean, you're going to get the same mean as what you started with. Okay. So anyone heard of the central limit theorem? If you've taken any statistics before. Okay. This is how we get the central limit theorem. And now let's find the variance using the same tricks. Okay. So basically, what's going to be the only thing that's going to be different here? When I pull out my 1 over n, how does it come out? Squared. And for the variance, we know what? If we want to add up random variables for the variance, we know that if they are independent random variables, that we can just add up each of the variances. So that's why in the problem statement I had to say that they were independent. So we have 1 over n squared times the variance of x1 plus the variance of x2 plus dot 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 all the way up to the variance of xn. Looking in the problem statement, what was the variance of each one of these random variables? It was sigma squared. So I have sigma squared plus sigma squared up to plus sigma squared. How many of the sigma squares did I add up? N of them, so we have n sigma squared. And what happens with those n's?
They cancel out part of it.
Okay, they cancel out part of it. So we're left with 1 over n sigma squared, or just sigma squared over n. Okay. Again, another very famous result, one we'll use when we start working like with the normal distribution and sample means, is that when you take the variance of your sample mean, you don't get the original variance, you get the original variance over n. So again, any questions here? So again, this is the second part of section 2.6. Okay. It's combinations and functions of random variables. What we did so far is we've done everything was linear functions. So I added things or I multiplied them by a coefficient. That was the only thing I did. Sometimes though we want to find functions of our random variables that are not linear. Okay, and the tricks that we just learned aren't going to help us with that. Okay, so for example, let's say we have a random variable x with PDF. Here's my PDF. F of x is 2x for x between 0 and 1, and that means it is 0 for all other x values. And my new random variable y is equal to the square root of x, and I want to find the expected value of y. Again, all these tricks that we just learned aren't going to help us. Okay? But we did learn one thing on the very first day when we did expected values. Okay. Do you remember anything that said the expected value for h of x, so if you have a function of your random variable, is you can just integrate h of x times the PDF? Do you remember that? We actually did use it on the very first day, just briefly, but we haven't talked about it again since then. So what this means is this means that if I want to find the expected value of y, which is really just the expected value of the square root of x, all I have to do is I integrate, but instead of putting an x here, because I want to find the expected value of x, all I have to do is put the square root of x and times it by the PDF, which is 2x dx, and integrate it, and I'm going to find my expected value for the square root of x. It makes it very, very simple. What are my bounds to integrate here? I'm going from 0 to 1, so I'm integrating again the square root of x times the PDF, because I want the expected value for square root of x, so I just put the square root of x at the beginning. If I put this in my calculator, I get 0.8. And we're going to just kind of go through these quickly so you see the pattern. So for this next one, again, we have a random variable, we have a new PDF, and now y is 1 over x. Find the mean of y. Mean of y just means find the expected value. But y is really just 1 over x. So when I integrate, what do I need to write down?
Over x covered.
1 over x times the PDF, which is my 1/2, and my bounds for integration are 2 to 4. So 0.346. This next one, I threw in just a little bit more. Okay, so we have, again, a random variable. Here's my PDF, so my f of x is 3x squared for x between 0 and 1. And y equals x squared. We want to find the expected value of 3y plus 2. So we want the expected value of 3y plus 2. But what is y? Y is really x squared. So instead of 3y plus 2, could I write 3x squared plus 2? How do you feel about that? And that means, what would I have to write down for my expected value? What do I need to integrate? I need to integrate 3x squared plus 2 times the PDF, which happens to be 3x squared. And I need to integrate from 0 to 1. And this gives me, no, I didn't calculate this one. $3.8. So are you seeing the pattern? Okay. So if I ask you on the test to find me the expected value for something that looks strange, all you have to do is put the expected value, or put what you want to find, times the PDF, and just integrate. So it's really not that bad, right? They try to make it sound complicated. It's really simple. So for my last one, we have a random variable x with PDF, again 1/2 for x between 2 and 4. And my new random variable, I called it z. Z equals e to the x. Find the expected value of z and the variance of z. So first of all, when I want to find the expected value of z, z is really e to the x. Which means, what do I need to write down for my integral? E to the x times 1/2. My bounds are from 2 to 4. Which gives me 23.6045. So that is my expected value for z. Even though, I mean, it was an exponential function, it looks really strange, still all I have to do is plug it in and it works out very nicely. Okay. What are your thoughts on how you could find the variance of z? Well, we know the formula. We know that if we find the expected value of z squared, then from the expected value of z squared and expected value of z, we can find our variance. Okay, so what would z squared look like if you try to translate it back into x's? So e to the x squared, which simplifies to e to the 2x. Okay, so now I just want to find the expected value of e to the 2x, so all I have to do is integrate e to the 2x times the PDF. Notice again, absolutely nothing is changing here. I still follow the exact same rules no matter how complicated my expression looks. So I get 731.59. And what is my formula to actually find the variance? Okay, the one we used over there, so I need to do the expected value of z squared minus the expected value of z quantity squared. So this is 731.59 minus 23.6 squared, which gives me 174.6. So again, at this point, this is all things that we learned how to do in section 2.3 when we first did our expected value. Okay. So how do you feel about this? Pretty good? It's really not that bad. You can do this on the homework, you can do this on the test. It shouldn't be anything scary. Okay. Now, this next part is something that will not be on the test. Okay, I'm going to ask you to do once on your homework, but it's not on the test. And it involves a lot more work, okay, to get the same results, but there are beneficial reasons to do it this way. Okay, so for example, we have a random variable x with this PDF. So f of x equals 2x from 0 to 1, and y equals the square root of x. So this is the problem we already worked on. Okay, notice here I did put a little x on my PDF, and that's just to remind myself that it is the PDF for my random variable x. Okay, the first thing I want you to do is find the CDF of x. So this is really a good review of everything we've done so far. How do we find the CDF from the PDF? We integrate. And what are my bounds? Well, I want to go from my lower bound to x, but I guess if I'm going to go to x, I should have a dummy variable. We'll use t. Okay, what should it give me? It should just be x squared. So my CDF, f of x, capital F of x, is x squared for what x values? What are my bounds going to be? My bound should still be from 0 to 1. So that's how I find the CDF of x. Notice we just found the CDF of x. I'm going to even put on here an x just to remind myself that it is the CDF for my random variable x. Because in the next step I'm going to ask you to find the CDF of y. Okay. So this is what we call the CDF method. It's not the only way to do this, but it's the one that's simplest without going into kind of like calculus 3 more. Okay, we want to find the CDF of y. So what we do is we say, well, if I wanted to find the CDF of y, I would write a capital F with a y on it to remind myself that it's y. Okay, and what is the definition of a CDF? So you say, well, I remember that this is the probability that y is less than or equal to little y. But then you're going to remind yourself, wait a second, earlier in the page I had a capital Y and I said capital Y equals the square root of x. Okay, so I'm going to replace that capital Y with the square root of a capital X is less than or equal to little y. Okay. Then what I'm going to do is I say, well, if I had this capital X by itself, then this would actually be the CDF of x. So what I'm going to do is I'm going to take this inequality and I'm going to solve it for my capital X. Okay, I'm going to solve it for capital X. What would I need to do? Square both sides. Does squaring something preserve your inequality? So is a small number squared going to be bigger or smaller than a bigger number squared? Okay. So we have the x is less than or equal to y squared. Okay. And we say, wait a second, that looks familiar. X less than or equal to y squared, that is the definition for the CDF of x. So really this is the CDF of x evaluated at the number y squared. Okay. And do we know the CDF for x? The CDF for x is x squared. So what we're going to do is we're going to plug the value y squared into that CDF. So it's going to be y squared squared, which gives me y to the 4th. So this is my CDF for y. Do you think that my bounds will be the same? Okay, because now we're dealing with y, so technically we should change our bounds. Remember in calculus when we do u substitution and we have to find our new bounds? That's what this reminds me of. So we're going to say if x equals 1, or let's do the 0 first for my lower bound. If x equals 0, then y would be what? 0 as well, because y is the square root of x. And if x equals 1, then y equals the square root of 1, which equals 1. Okay. So my bounds are, in this case, by coincidence, the same. So my CDF of y, f of y, is y to the fourth for y values between 0 and 1. Okay. So this is the CDF method. Okay. Again, it's just a way to change from the CDF of x to the CDF of y. Okay. Once you have, so again, this is why I said it's kind of a nice review. Once you have the CDF of y, how would you find the PDF? Do you remember how we go from CDF to PDF? Differentiate. So fy, little f of y, the PDF, is just going to be the derivative of the CDF. So the derivative of y to the power of 4 gives me 4 y cubed. And again, what are my bounds going to be? For y between 0 and 1. So we went from the PDF of x to the CDF of x to the CDF of y back to the PDF of y. Seems like a lot of work, but we got here. And now they want us to find the expected value of y. How do we find our expected value of y? We just need to integrate y times the PDF of y, which is 4y cubed, for all my bounds from 0 to 1, dy. Let's see what this gives me. It gives me 4/5, which is 0.8. Okay. Look on the previous page. What did we get when we did it the old way? We got 0.8, so it's the exact same thing. Which method was easier? Okay, the first one, by far, right? Okay, so I was sitting here thinking about this last night when I was making your notes, and I was like, well, why do we care about doing it this new way? Okay, and the true reason that you care about doing it this way, of actually finding a PDF or CDF for y, is because you might actually want to find probabilities. And even though we had ways to find the expected value for functions of x easily, we don't actually have formulas to find probabilities for a function of x easily. Okay. And so if you want to find probabilities for like the square root of x is bigger than 0.3, or that y is bigger than 0.3, you actually need to know something about the CDF or PDF of y. So that is the true reason that we have this way to transform our random variables, is so that we can find our probabilities. So for example, this find the probability that y is greater than 0.3. This was originally the probability that square root of x was greater than 0.3. Okay. And so to find that, it's easier if we find the CDF or PDF of y. Okay. Or it's one of the reasons that we might want to do this. Okay. So what are your thoughts? How would you like to find this probability? Okay. So ignore the fact that it's the square root of x, because we know now we found the CDF and PDF of y. So do you want to find the CDF or PDF to find this probability? You can use either one. It's not a right or wrong answer. Okay, someone said CDF. Let's use the CDF. The CDF is y to the fourth. Excuse me. For 0 less than or equal to y less than or equal to 1. Okay. So what does this look like? How do I need to find this? Find the probability that y is greater than 3. It's been a little while. What do I need to do? Okay, well, let's remind ourselves, what does it do for me if I just do f of 0.3?
That gives you the probability that it's 0.3 or higher.
So let's see, f of 0.3 itself would give me 0.3 or less. So CDF is always cumulative, so it's always the probability to the
Oh, we have to
left.
do the probability of, yeah, f of 1 minus f.
Okay, so we can do my upper bound minus my 0.3. So this is going to be 1 to the power of 4 minus my f of 0.3, so 0.3 to the power of 4. .9919. So it turns out that's actually a pretty big probability. So, questions on this problem? Okay. How did you feel about the CDF method? It's probably, I think it's one of the more complicated things we've done so far. Let's skip that one. Let's go to example 7. So again, I'm going to skip example 6 because it is something that you're not going to have on the test. So I think we'll move on. But we can go to example 7. Try this just once more. So we have a random variable x with, this is my PDF, and z equals e to the x. Find the CDF of x. So first find the CDF of x. So to find the CDF, what's the rule? I need to integrate from my lower bound to x. I need to integrate my PDF, and I use a dummy variable. So it gives me 1/2 x. What are my bounds? For x between 2 and 4.
Doesn't that mean in your integral you should have 2 as your lower bound?
Yes, I wondered something was going to be strange. Thank you. I get so used to the zeros. Let's try that again. So it's going to be 1/2 times x minus 2. Do you want to know what, so before you said it, what clued me into the fact that something was wrong? Okay. I know that my CDF has to be 1 at its highest point. The cumulative probability must add up to 1. And before, when I just had 1/2 x, I realized, well, if I put in the x value of 4, I would have gotten 1/2 times 4 was 2, and I realized that my CDF of 2 is not a valid answer. Okay. So that was what I did wrong, was we forgot to put 2 as our lower bound. But now we have our f of x, and my bounds are for x between 2 and 4. Okay. Now we find the CDF of z. So to do this, we say, okay, I want to find the CDF of z. That is defined as the probability that capital Z, my random variable that's unknown yet, is less than or equal to a specific z value. But I say, do I know anything about capital Z? We know that it is e to the x. Okay. And at this point, once you get here, you say, well, I want to solve for x. Okay, so I need to use the logarithm, so this is going to be the probability that x is less than or equal to what? The natural log of z. Okay. And at this point, I say, well, this is just an x less than or equal to. That is the definition of the CDF of x. So this is the CDF of x evaluated at the specific value, natural log of little z. So if you want to take the CDF of x and evaluate it at that specific value, you just plug that specific value into your CDF, which we just found previously. So this is natural log of z minus 2. Now I need to figure out what are my bounds. Okay, so to do this I say, well, if x equals 2, then z equals what? Z is e to the x, so e to the 2 gives me 7.38. And if x equals 4, z equals e to the 4, which is 54.5. So what are my new bounds for my CDF of z? So this is my CDF, and it is for z values between 3.8 and 54.5. And again, how do I go from the CDF of z to the PDF of z? I need to differentiate. My CDF, so my 1/2 natural log of z minus 2. Let's see. Is that right? Oh, no, it's not right. So I need to take the derivative of 0.5 times the natural log of z minus 2. So it gives me 1 over 2z. That sounds better. And what are my bounds? Again, they are for z between 7.38 and to 54.5. So, any thoughts or anything to here? Now if I want to find the expected value of z, what do I need to do? I just need to integrate z times its PDF, so 1 over 2z, from 7.38 to 54.5. I wonder if I did something wrong with my bounds. I think I did something wrong with my bounds. Or we did a algebra mistake somewhere. Because that's really big.
I got 22.
Oh, you got 23?
Yeah. 23.605.
Okay, so you guys all got 23.6 when you typed it in like that? So I must have just typed it in wrong. Okay, and I like this answer a lot better. Why?
Because it's close to the other one.
Because it's close to the what I got when we did it previously, the very short way. Okay, because it should be the same either way that I do it. And finally, if I want to find the probability that z is between 2.3 and 3.5, there are two ways I could do this. I could use the CDF or I could use the PDF. Let's go ahead and use the PDF just because we used the CDF last time. So how do I do this using the PDF method? I have to integrate Actually, what is this going to be? I want to integrate from 2.3 to 3.5, but what is my PDF for those values?
287.38.
Okay. What my PDF for these x values is 0, which gives me 0 because it was outside my bounds. Which is okay. I guess you could be given a problem like this and you can tell them that your answer is 0. Makes it very simple to calculate, right? Okay. So, questions?